Okay, thank you for the invitation. And I'll be talking, so I'm studying the physics of machine learning at Facebook AI Research. But in previous my academic life, I was also studying glass, and then that's what I'm supposed to talk about today. So the complex landscape, which is the theme of this conference, governs many things in everyday life. So prototypical example is the glasses and also plastic and sand. But also these days, people study like biological tissues and ecosystem. And some people said that also the machine learning is governed by complex landscape. So having this mixed audience, I think my hope is that I would just focus on glass and plastic and sands today. But the methodology I will describe will maybe carry out or may inspire something new in a different setup like machine learning. Okay. So here's the outline of my talk. First, I'll review the glass phenomenology, and I'll describe something called the amorphous order, which is captured by point-to-set correlations. And then finally, if time permitting, I'll describe something that happens beyond the glass ceiling. Okay, so please ask questions. Otherwise, it's going to finish within like 20 minutes. So, and also, okay, I'm assuming that half of the audience, or order one fraction of this audience, is machine learning people. So I'll try to introduce the basic concepts pretty easily. So hopefully you understand. You can talk to glass colleagues for the next 3 months. Okay. So here's the typical equation of state you see in a textbook. So entropy density as a function of temperature. So at high temperature, you have a liquid phase, and you cool them down. You go through the first order transition at melting temperature, and you get the crystal phase. So that's a typical thing you see in a textbook. But something that's not often discussed in the textbook is something called supercooled liquid phase, where you can actually cool down the system below the melting temperature while staying in a quasi-equilibrium state. And that well, actually for the complex enough molecules, that's a pretty typical phenomenon because it's hard to crystallize the like complex molecules. So the name sounds awesome, but it seems like a just boring continuation of liquid phase down to low temperature. So why would you bother to study them? So to answer that question, let me look at the dynamics of this system. So here's the shear viscosity as a function of temperature. So shear viscosity basically measures like how that time scale in your system. So the more viscous it is, the more time it takes for the system to respond. Okay, so honey is pretty viscous. Like if you try to put the jar upside down for the honey, then it takes a long time to fall out. Whereas like for water, it's smooth, so it's going to just go down. Right. So here are the numbers for the typical molecular liquids. So usually at melting temperature, it starts as smooth as water, but then as you cool the system down, it quickly becomes as viscous as honey. And by the time like you're 30% down from the melting temperature, the viscosity has grown by 15 order magnitude, which is a lot. Okay. So if you translate these numbers into the time scale, then even if you like start at the picosecond at the at melting temperature, by the time you reach this 10 to the 13 pores, it reaches the equilibrium time scale being like 100 seconds, which start to compete with your sense of patience, right? Like you don't want to do the experiment more than like 100 hours, and that would take a pain of graduate students, so you don't want to do that. So this defines a glass ceiling that you cannot go beyond, practically. And if you revisit the equilibrium state I've shown before, then like you have liquid phase upstairs, and then you cool down, but the viscosity goes up. So at some point, the equilibrium time scale is like very long. So if you keep cooling the system at the same rate, at one point you fall out of equilibrium, and that's a glass state you see everywhere, like there and here. Okay. So that's the glass phenomenology. So why do we still talk about the glasses these days? Like, isn't it pretty obvious like how it works? So we've seen that at high temperature you have smooth liquid, it becomes really sluggish, and at one point it even becomes a solid state. So surely if you could look at the molecular structure, then you may see the very different structure at the microscopic scale. But that's not what we see. So if you look at the molecular configuration at the very disparate temperature scales, like you see basically the same mess. So this leads to the question of whether we can have some kind of order parameter for this kind of materials. Any questions so far? Good. Oh, by the way, some people study the smooth to sluggish slowdown, and some people study like transition from sluggish state to the solid state, and some people study the solid state property. One I'm going to be focusing on would be purely in this regime where you go from smooth to sluggish. Okay. So to just summarize what I have discussed, basically Glassy slowdown is the following thing. It's a dramatic slowdown as you cool down the temperature without having any structural changes. So for example, if you look at the two-point function of density, then it doesn't change at all. Okay. So this question has been unsolved for like 70 years or more. So many people have like proposed many theories, like mode coupling, locally preferred structures, dynamic facilitation, and energy landscape. And I'm going to be focusing on energy landscape because that's what I believe in, and also this is the theme of the conference. Okay. So here's the basic picture. Basically, you draw the energy landscape as a function of configuration. So each point on this x-axis corresponds to a particular molecular state. So a bunch of dots are molecule position of molecules, and they just have amorphous configuration. And at the short time scale, like these molecules just vibrates around. So in energy landscape picture, it just vibrates around the local minima. But at the relaxation time scale, like these states try to jump over the barrier in a high dimensional landscape. And this in a real space corresponds to a bunch of molecules rearranging cooperatively together. So that defines a length scale, which is usually called dynamical length scale. And since this is a pretty rare event, so you have to rearrange the molecule at the same time in a particular way. So it takes a really long, it's a rare event, so it takes a long time, and it has this somewhat activated process formula. So you notice that even if this C, the length scale of these things that move together, grows by a tiny bit, it's in exponential. So that kind of leads to the very quick, rapid expansion in viscosity or relaxation time. So that's what we think is going on in a Glassy system. Okay. So this notion of the energy landscape has been pretty nicely worked out in a mean field limit. So Mark discussed the spin glasses in a mean field setup, but then once you go into the finite dimensional worlds that we live in, then this kind of picture kind of start to be problematic. So for example, for the molecular system, this kind of rearrangement, if you in a microscope sample, is happening all the time, right? So you're really never at the local minima, but you're always jumping around in this energy landscape. So how do we make sense of that? How do we make this notion of landscape precise? And the notion of pointer set correlation, which is what I'm asked to talk about today, is the one to make this notion precise. And this is introduced by Giulio Biroli and Bouchot in 2004, and then Montanari and Simarjan made it more precise. Okay. The basic idea is that rather than look at the landscape as a whole system, you kind of slice out the small chunk of the landscape and you look at the behavior of these things. Okay. So since this notion of pointer set correlation is not so common outside the Glassy physics community, let me define it for you. So here, like first you take a molecular configuration from like Boltzmann ensemble. X1 is a bunch of molecules. So take a snapshot of your system. Now what you do next is that you take a cavity of some size R, and then you fix everything outside. Okay. So X1 out is the bunch of molecules outside this cavity, and it's fixed once and for all, or once for now. And then you fill in the particle inside the cavity, and you try to resample the configuration inside the cavity while keeping the outside configuration intact. Okay? So X1 out is fixed, and X2 in is the new things that you kind of like resampling inside. And note that you see this force from outside, which is kind of disorder source. And this is like a spin glass disorder. Okay? And finally, after doing this resampling, you compare this new configuration to the old configuration and ask how similar they are. And to quantify this, you can define something called overlap, which is also discussed in the Mark lecture. Basically, as in the spin system, it says that it's like 1 if it's similar, and it's 0 if it's dissimilar, and in between if it's in between. Okay, I can write down the formula, but it's not insightful. Like this suffice for this lecture. Okay, so since this is not a common concept, let me repeat again. So first, you take a snapshot. You take a cavity, fix everything outside, and you resample the thing inside again, which is drawn from the conditional Boltzmann ensemble with the fixed outside, and then you compare the original configuration and new configuration and ask how similar they are. Okay, so far so good. So what do you expect for this quantity to do? So if you take a very small cavity, then at the time you fix everything outside the cavity, then basically what you have inside is dictated by that environment. Okay. So here's the landscape for the particle inside the cavity, and it basically got like one minima, and then just it's oscillate around that minima. So this blue is kind of water level that depicts how it's occupied by the conditional Boltzmann ensemble. Okay. So in this case, like it's always like basically similar to the original configuration, so the overlap would be pretty high, like close to 1. Okay. Let's take the other extreme. So like you take a very large cavity size, then like when you try to resample the system inside the cavity, then you're basically getting the independent sample. So there's no reason for you to expect that these two configurations to be similar. So oftentimes you have very complex landscape, and if you resample, so let's say this is the original configuration, the probability of being in the same state is basically negligible. So basically overlap would be low on average. Okay. So if you take an intermediate length scale, then maybe you have a few, not too many, not one, but then a few metastable states. So in that case, sometimes you end up in the same state, sometimes you end up in a different state. So if you average over, you get some medium number like 0.5, less than 1 or 0. So you see that as you change the length scale of this cavity, you kind of have a crossover from having one state to a few states to many, many states. And that's a point-to-set length scale that people sometimes care. Okay. And note that this is a temperature-dependent length scale. So at the high temperature, you have a bunch of states. So as you even if you have a tiny cavity, you have access to all the states, or many states. But if you are at low temperature, there's so much fewer metastable state that you have to go to a longer length scale to access a new state. So this length scale would be longer at the low temperature because of the rarefaction of these metastable states. Okay. So this is all theorists talking, like, is it real? And physics is empirical science, so you have to kind of confirm whether this hypothesis that the point-to-set length scale grow and hence the Glassy slowdown happen is true or not. So the easiest way nowadays is to do the simulations. So you think that you can do the simulation, you see this, and then you'll be happy. But there were like no reliable measurement for a decade or so. And the reason is the following two. So first of all, the Glassy system slows down very quickly. So by construction, you have the long computational time scale. So it's a pain in the ass to measure the Glassy state at low temperature. So on top of that, like when you try to confine the system in a cavity, it gets more like kind of pressure from the outside. So it becomes even slower than the Glassy system that was already slow outside. So there's this double increase in the time scale, and it lets you like kind of not measure the point-to-set length scale reliably. So the trick, long story short, we have overcome these obstacles by using parallel tempering. So the basic idea is that you have this rough landscape. If you do the usual local Monte Carlo sampling, you kind of end up like sampling here. But if you do the parallel tempering, you basically pour the water into the mountain, and you go high up, and then go down and up and down in a controlled way, such that you kind of sample all the minima in a reasonable computational time. So if you don't do parallel tempering, you get stuck, and then you may think that you have only one state, but then in reality, you may just miss these different states. Okay. So with this methodology developed, we can bear out the theoretical hypothesis we had, or theoretical picture we had. So when the cavity is small, we had this simple landscape picture. The overlap would be pretty high. And here's the histogram of the overlap within the cavity when the cavity is small. So basically, it takes a value close to 1 all the time and oscillate around that number, which is in line with the physical picture you have. And the other extreme, again, like if you take a really large cavity, you have this bunch of metastable states, so you have a bunch of dissimilar states. So basically, the overlap peaks around 0, because you're always almost sampling the independent states. And the interesting thing, again, happens at the intermediate length scale. So here, you have, sometimes you end up in the same state, so that gives rise to this bump. And then sometimes you end up in a different state, so that gives rise to this bump. So you have this kind of neat bimodal structure that's kind of that's pretty decisively telling you that you have this landscape structure. Okay. So this is
why bimodal? Why if you end up in different?
So if you end up in a different state, basically you look very dissimilar to each other, so you're like overlap 0. And if you're in the same state, then it's like overlap 1 or close to that. So that's why you got. And then this structure, this kind of bimodal sign signature becomes more evident as you go to lower temperature. Okay. Any other questions? Great. So so we had this picture, 1 to few to many landscape, many states, and we kind of bear out by measuring this histogram of overlap. You bear out this picture, and you can say that this system at this length scale smaller than the pointer set length scale, is governed by amorphous order. So it's like an order state in a sense that it's kind of dictated by the environment you have, but the environment itself is amorphous state. So each time, like this order is kind of amorphous. So it leads to this name, amorphous order, which seems like an oxymoron, but that's the way it's called. Okay. So if you got this message, then you're basically good to go. Okay. So let's have fun. So once you develop this methodology, you can do many things. So first, so one thing to do is that you bear out the fact that this length scale also grows as a function as you go to lower temperature. So this is 1/t. So if you go to lower temperature, that's like this way. And I postulated that if you go to lower temperature, then you have fewer and fewer metastable states. So you have to go to longer distance to access the new state. Hence, this length scale should grow. And that's what we see. So this is green line. So this blue line is the pointer set length scale. And this green line is the 2-point length scale that's measured by density 2-point function. So 2-point function length scale doesn't grow, whereas pointer set length scale grows. So I would say that the ratio between them growing is a way to define that whether you have a Glassy system or not. Okay. And you can do more things with this. So you can kind of relate the statics and dynamics now. So let's say that you have measured pointer set length scale. Now you can kind of shift this center of cavity throughout the system. Okay. So some places may have like few states, some places have two, but then some places may have many states already accessible within this cavity size. And when that happens, then since you can easily jump over these states by arranging things inside here, so you think that if overlap is small, then the dynamics will be fast. In contrast, if you have some place where even having this relatively large cavity scale leads to only one state accessible, then overlap will be still 1. So reversing the sentences, you said the overlap is high, hence you have access to only 1, so it should be slow. And you can actually measure the correlation between the overlap and how fast these regions react over time. And you see that there's a correlation between 0 fast and 1 is slow. And this is motivated by Hockey at our work, and then we measure this more directly using our methodology. Okay. Okay. So the basic message that you go to lower temperature, you have rarefaction of metastable states, a fewer states, and it leads to the dramatic slowdown of Glassy system, and point-to-set correlation is a way to capture this relation between the two. Okay, good. So here's a bonus stage. So, or the recent progress that we made with Montpellier group. So if you understand everything up to this, then it's fine. Just enjoy the last part. Okay, so typically in a glass simulations, like we used to cover only about 4 or 5 decays in simulation. It used to be worse. It used to be like 2 to the 3 decays. But due to the hardware development, we came to 4 to 5, but that's still small. In a colloidal experiments, so a bunch of sands or like a bunch of disks in your desktop, you have 10 to the 5 dynamical range covered, and then, but the molecular system, as I described, had this 15 order magnitude. So if you want to catch up with the real experimental situations, it's going to take a century to get there. But recent progress made it possible that the simulation to actually catch up with the experiment and even go beyond what was accessible before. And the basic message, so it's called swap algorithm, but the basic message or motivation behind this algorithm is that usually you take a system and you try to make your optimizer or sampling algorithm much better to sample more. But the trick was that you also engineer the system so that it's going to be good, sampled well by the optimizer you have. So you kind of tune the both and then get this humongous speed up. And in our situation, we also had a caveat that you have to also still retain Glassy physics, and we make sure of this by measuring point-to-set, or the decorrelation between 2-point length scale and the point-to-set length scale. So, so here's a plot. So basically, this y-axis is what's called configurational entropy, and it's a measure of entropy, and the point-to-set length scale is basically inverse of this. So point-to-set length scale growing means that this quantity vanish, right? So here's what was accessible before by experiment, and by this swap technique, we can go catch up with the glass experiment, and now a little bit over beyond the glass ceiling. And the message of this paper that we published was that this picture that the rarefaction metastable states drives the Glassy slowdown keeps happening even below this glass ceiling. Some people are conjecturing that maybe it's going to stop around or like beyond the glass ceiling, but that's not the case. So it's more evidence that this picture is a correct way to think about it. And another thing that we did is that actually this swap algorithm also applies in 2 dimensions. And there have been like many discussions that the 2-dimensional Glassy system is really different from 3-dimensional of higher dimensional counterpart. So we thought that maybe we should investigate what's happening there. And what we saw is actually that this point where the point-to-set length scale diverge or the configuration entropy vanish is not at finite temperature, but precisely at 0 temperature in 2D. I think it's pretty cute observation. Assuming that it's true, and it calls for like some like very simple theoretical argument that says that maybe this is the lower critical dimension of some sort for the Glassy system. But yeah, hopefully, yeah.
You said you were tuning both the algorithm and the system to retain all the Glassy physics. Can you say a bit why you which subset of kind of systems you?
Yeah, so first thing so this was the work by Montpellier group, and what they have done is that first you look at the hot spheres, and you have some polydispersed system. So the diameter of the particles are different from particle to particle. Now you can try to tune the distribution of this parameter, diameters, right? So they tune this diameter distribution, and you kind of make it wide, enough that this swap of particle happens more often. So swap was before used for like two particle system, like binary system. But then it was pretty hard to swap the system when like it's very jammed. And then if you try to swap the small particle to big particle, it was not accepting that move. So the trick was to introduce some chain reaction of this swap by having the continuous distribution, and you engineer a little bit more about the distribution, and you get this speed up. Yeah. Okay. And later they did also source spheres and so on. So it kind of is pretty generic once you have polydispersed system. And some people are doing 4D, 5D, 6D as well. Yeah.
I guess it eases the problem by changing it doesn't change the complexity.
So that's why we measure this point to set thing. So this measures the complexity of, well, if you meant in a technical sense complexity, then, no. So it's pretty simple algorithm. It just said have like 20% of the Monte Carlo move is spent by just trying to swap the particle and then use the Metropolis criteria. So it's nothing computationally. Yeah. Okay. Good. So in summary, Glassy Slowdown is pretty cool and puzzling, but this point to set question tried to unify try to solve this problem by postulating this amorphous order is captured by point to set lengths or point to set correlations, and it seems to be working. So again, real functional meta state drives this decorrelation of length scale, point to set to 2-point correlation lengths, shear viscosity grows. And also, in addition, you can actually do the local probe of this local amorphous order, and it turns out to be a good predictor for the local dynamics. So this kind of relation, between static and viscous dynamics holds even at the local level. And then something that I didn't allude to much is that this phenomena of point to set lengths growing is pretty universal. Like we've done this for many systems, and unlike any other proposal, it seems to work all the time. And recently tested beyond the glass ceiling, so that's the end of the talk.
Questions? Okay, perhaps I have a simple question. So how do you check for equilibration in your
So that's something we made really careful study of. So one thing you can do is that you can first study with the original configuration and equilibrate using this prior tempering. But you can also start with the randomized configuration and equilibrate. Now, if you do a very bad sampling method, then they might actually asymptote the different value of overlap. But we make sure that if you do prior tempering, then at long time it asymptotes the same number of overlap, making sure that you kind of transition well.
So this is inside the cavity.
Inside the cavity. Yeah, because if you have like only 3 states or 2 states, let's say, then if you randomize and then you end up in a different state, you may not access, but that makes sense. Yeah.
Other questions? Okay, if not, we thank Shaw again.